Right, any questions so far? Okay, so we will just make it more general, and this will be somewhat important. We'll look at codes for this, but basically the idea is you can generalize this Markov thing, right? Where the Markov thing we said was given the previous symbol, you don't have any dependence on the further past. Kth order Markov means that your current symbol just depends on the previous k symbols. If you know the previous k symbols, that is all you need to know. Knowing the further away past doesn't matter, right? So if you like to think in terms of like prediction, so what we are saying is un minus 1 through un minus k is enough to predict un. Like knowing things even before n minus k won't really help you in predicting un better, or like knowing the distribution better. Let me just read through the definition. So a kth order Markov source is defined by the condition probability of un given its entire past is same as the probability of un just given the last k symbols for every n. In words, the conditional probability of un given the entire past depends only on the past k symbols, or more precisely, un is independent of the past older than k symbols given the last k symbols, right? So knowing the last k symbols is the best predictor for un. So we saw that in stationary sources you could have like arbitrary time dependence, but in kth order Markov source you have just past k symbols you depend on, and then so if you are like generating this, you take the last k sequence, you generate the next one, then you take last k, generate, so on. So most practical stationary sources can be approximated well with a finite kth order model, and you can go higher k and then you get a better approximation with diminishing returns. Okay, any question on kth order Markov sources? It's a generalization of first order, like the normal Markov source we just saw. So just to like, when we just say Markov, we usually mean first order, and when we say IID, we mean zeroth order, because IID is like, you just depend on nobody. So k is 0, right? You don't need to know any past to predict the future. Okay, let's quickly look at a non-example of a, I guess I told you the answer, but say you're at a bus stop, right? Which is like reasonably regular. Buses arrive at roughly 15-minute frequency. And like these are, let's say, the bus timings, 4:16, 4:28, 4:46, 5:02. Is this a stationary process? Is this sequence of times, bus arrival times, is this stationary? It is definitely random, right? Because buses have some randomness in when they exactly arrive. But is it stationary? Is it IID, first of all? Is it stationary? So what are the properties of stationary processes? Among other things, we heard that the mean doesn't change with time. So do we think the average bus arrival time keeps, like if the first bus is expected to arrive at 4 p.m., is the second bus also expected to arrive at 4 p.m.? No, right, it's expected to arrive at 4:15 and the next one is like 4:30 and so on. So this is not a stationary process, right? Like in particular, the mean increases with time. Okay, is that clear? That this is not stationary, right? Because just buses, not all buses are supposed to arrive at the exact same time. Okay, can you convert it to a stationary process by doing a simple transformation? Yep. Yeah, so again, the answer is just take the difference, right? This is like surprisingly common. Like in real life data, you will see a lot of times, like we will see a lot of compressors, this lecture, next lecture, so on. All of them will work wonderfully on stationary sequences. But if you give it a non-stationary like this, they just start failing. like you take the best, like state-of-the-art, like Z standard or one of these compressors, you give it a file which has like 1, 2, 3, 4, 5, 6, just a sequence of numbers, which is trivial to predict. Like, you know, the previous one, you just do +1, and it will just do a terrible job at compressing it. But if you just like do this delta coding or this difference between the consecutive ones, it just becomes a sequence of like very similar looking values, and then suddenly the compression improves, right? So again, very important to like, that's why this theory is important, right? Like, you understand where do these compressors do well, where do they not do well, and when they not do well, can you convert it into a different sequence, right? So here again, you do the delta or the diff, right? You just take this difference, right? So you just do like 428 minus 416. This is like 12 minutes, right? This is like the, if you have done like process, this is like an inter-arrival time, usually modeled as a exponential distribution in theory. Right. Okay, let's move on to information theoretic quantities for non-IID random variables. If you have no questions. Right. These you will see in your homework. So I guess hopefully this will help you with the problems. So we saw the entropy, right? I hope everybody remembers entropy of U was, we did like PU log 1 over PU over all the U's, right? This was the entropy. So here we define the conditional entropy of U given V. So now we have two random variables, U and V, which are not necessarily independent. And this is defined as this thing. This is the, you can write this as expectation of log 1 over PU, right? But, so similar, very similar formula. Good. Okay, and then you can expand it out. We will try to do one example in class. So you have, this is just the definition of the expectation, nothing very clever here. Second step, we use the chain rule. So we do PUV as like PV multiplied by PU given V. And then you take this big thing and you can write it like this. So really we are defining two quantities. We are defining two quantities. So one is this thing, which is this you can like read as conditional entropy of U given V is equal to V, right? So if you know that V is equal to small v, then what is the conditional entropy of U? And this one is nothing different from what you have already read, right? This is just the entropy of, if you take this distribution, U given V equal to V. This one you have already seen. So let's say, for example, right, if V equal to V implies that U is like Bernoulli half, for example, then the entropy of U given V equal to V, somebody tell me what is the answer? What is the entropy of Bernoulli half? 1, right? So this one we are very comfortable with. We have seen this a million times, like this sort of simple thing where, not a million, but like a few times now. Okay, and then the second thing we define is this, which is the just conditional entropy of U given V. So this is an average of the above quantity. So this is like on average, what is the conditional entropy of U given V? And therefore it is defined as PV HU V equal to V, sum over V. Can somebody remind me what was the intuitive meaning of entropy? Like if entropy is high, what does that mean? Yeah. Exactly, right. So entropy was a measure of uncertainty. It was a measure of randomness, right? If it's a constant, it's zero entropy, uniform maximum entropy, right? So can you guess what is the meaning of the conditional entropy of U given V equal to V, based on what we know about entropy already? So let's say knowing that V equal to V, small v, makes U deterministic. Then the entropy will be very small, the conditional entropy, right? So the conditional entropy is really, the uncertainty left in U, or uncertainty in U, given that you know something about V, right? So this thing is a measure of uncertainty in U, given that V is equal to V, right? So if you know the value of V, what is the uncertainty in U, right? And this guy is the average uncertainty in U given V, basically. So on average, if you know V, how much uncertainty do you have about U, right? So just to like think of an example. For example, you have like you're playing like this murder mystery type of game where you like have suspicion on a bunch of different suspects, right? So that is U. U is the variable that represents who is the murderer, okay? And then you keep getting specific clues, right? So maybe you get some fingerprint clue. And maybe that will change the uncertainty in who you think the murderer is, right? You will find that some clues will increase your uncertainty. Like earlier you thought, oh no, I think this guy is the murderer. But then you see this clue and then it confuses you again, right? So what you will see is that this quantity can be bigger than or smaller than the entropy of U. Knowing a specific piece of evidence can increase your entropy or decrease your entropy. But you will see that on average, knowing more can't hurt you. The more you know about V, it will never hurt you in terms of U. So it will decrease your uncertainty, right? So as you play this murder game, over time as you get more and more clues, your uncertainty will keep reducing. And if you are a good detective like Sherlock Holmes, you will converge on the correct culprit. Okay. Any questions? Okay, let's try to do this example. So you are given this distribution. This is a joint distribution between U and V, right? So the way this is written is like this cell is probability that U is 0 and V is 0, right? And this cell is like U is 1, V is 1, right? So if you read this, and I would encourage you to do this carefully at home, is that you will see that U is actually uniformly distributed in 0, 1. And knowing that U is 0, so that is the first row in that table, means that V has equal probability of being 0 or being 1, right? So what is the formula we use here? It's like this guy. V equal to 0 given U equal to 0 is simply PU equal to 0, comma V equal to 0 divided by probability that U equal to 0, which is like 1/4 divided by 1/2, which is 1/2, okay? And if U is known to be 1, then you see V has no uncertainty. V is definitely 1. So if U is 1, then V is 1. Right, so this is simple stuff, okay? Can we try these? Okay, so what is the entropy in V given that U is equal to 0? So U is equal to 0. Yeah, entropy in V given that U equal to 0. It's 1, right? Why? Because we saw that if U is 0, then V is simply Bernoulli half. So that has entropy 1. What about this guy? Entropy in V if U is equal to 1. It's 0 again. Why it's 0? Because this is deterministic. Knowing U equal to 1 definitely tells you V equal to 1. And now we'll just calculate the entropy, the average of these quantities, which is PU equal to 0 times HV given U equal to 0 plus PU equal to 1 HV U equal to 1, and then you can do like half times 1 plus half times 0, because we saw that U is Bernoulli half here. So this is just half, okay. And a few things I computed at home was that the entropy of U is 1 because it's Bernoulli half. Entropy of V is 0.811. So you already see that the entropy of this guy is bigger than equal to this. So you see that knowing U has decreased your uncertainty about V. Right? So knowing just V on its own had some uncertainty 0.811, but knowing U reduced it to half. Right? But you see that if you know U equal to 0, that actually increased your uncertainty. Right? Because knowing U equal to 1 reduces your uncertainty about V. Knowing U equal to 0 increases your uncertainty about V, and then on average, it still gets lower. And this is a calculation that you can do very easily, which is like, you just take all 4 things in the table and do like this sort of thing. So half plus half, I think it will be 3 by 2. And you can verify that this is actually equal to this thing, HU plus HV given U. So this is the chain rule for entropies. So the joint entropy of U and V is actually equal to the entropy of U plus the entropy of V given U, right? So the overall uncertainty in U and V combined is the uncertainty in U and the uncertainty in V given U. Right. So, few properties about conditional entropy. First is that conditioning reduces entropy, which is that entropy of U given V will be less than or equal to U with equality if and if U and V are independent. So if U and V are independent, they will have the same. So knowing anything about V will tell you nothing about U. And this is the thing I was telling you earlier about, like a specific piece of evidence can increase your uncertainty, but on average, knowledge will always reduce your uncertainty. Knowing things is good on average. Okay. Let me just show all the properties at once. Okay. Then we have the chain rule of entropies, which is this. That the entropy, joint entropy is, if you remember the chain rule we saw before for IID, if you recall, not IID, just for independent, the entropy was like sum of these entropies, right? But for non-IID, in more general case, it is actually this formula, like HU plus HV given U. Let me like quickly state it in terms of compression, because that's the class we are in, right? So you remember HU was the best thing you can do for compressing U on its own. HV was the best thing you could do for compressing V on its own. And in fact, HV given U is the best thing you can do for compressing V if you know U. So this is like the minimum number of bits you can use to compress V if you knew U, right? So what we are saying is, if you want to jointly compress U and V, what you could do is you first compress U on its own, and then you compress V given that you know U, right? So it's like a two-step compression process, where first you compress just U and then you compress V given the knowledge of U. So that is, and the bits add up basically, right? So maybe this guy uses 1 bit and this guy uses like half bit. And so overall you get like 3 by 2 bits for jointly compressing U and V. And the last thing which you see here is saying that the joint entropy between in U and V is either equal to or smaller than the sum of the entropies, which means that if you independently compress U and V, so let's take an extreme example, right? Let's say you had a random variable which was like either 1 or 0, and then you had a second random variable which was always the opposite of the first random variable. So if the first random variable is 1, then the other guy is 0. If the first one is 0, the other is 1. So if you compress them independently, they will take 1 bit each. Whereas if you use the knowledge of the first guy to compress the other guy, then you can compress the second one for free, right? So I hope this is somewhat, right? So if we do this example, simple example where if U is Bernoulli half and V is like 1 minus U, right? So HU will be 1, so will be HV, but the joint entropy of U and V is actually still 1. So this is like less than HU plus HV, right? Here, like knowing one of them basically tells you the other one. So compressing them jointly is much better than compressing them independently. So that is sort of the whole idea about this, all of this, right? There is a question in the quiz. There is a question in the homework. So do those, and I hope you will get like very comfortable with these quantities. Any questions? Okay, just in general, you can have this condition on the past n things instead of just conditioning on the past thing. Great. Any questions? Okay. Now we define like the real quantity for stationary sources, which is that what we want to do is we had entropy, right? We know entropy was the best thing you could do for compressing IID sequences. Now we want to compress stationary sequences or Markov or any of these guys. So we will define something called entropy rate, which is defined for any stationary process, right? And not only one, but two ways of defining it, right? So you like sort of buy one, get one free sort of deal. There are these two definitions. We won't go into the proofs. We won't go into very specifics, but basic idea is that entropy rate of a stationary process is defined in two ways. First way is you take the past n symbols, you compute if you know the past, how much is left in the future, basically. That's what you're trying to do. So if you knew the first million symbols, what is the remaining entropy in the next symbol? How much is each next symbol adding, basically the uncertainty? That is your entropy rate, and it's defined like this. This is the limit. The second way to define it is, again, you can think in terms of compression. If I want to jointly compress n symbols at a time, and then take like the per symbol, how much am I paying for compression? And then you take the limit. So you make the blocks bigger and bigger, bigger and bigger, and you see like per symbol, how much do I need to pay for compression? So there are like two ways of defining it, and in fact, you can show that these two are equal for any stationary process, and the limit is called the entropy rate. We won't have that much use for it. Really, I think if you want to remember one of these definitions, remember this guy. This is the main one. This is the one we'll use more frequently. This is in terms of like how much extra. Let me write it down. So this is like on average bits per symbol for large blocks, right? And this one is additional entropy per symbol given the past, right? So how much each symbol, how much extra entropy is it adding to your thing? And we'll look at a couple of examples in a minute. Okay, I guess we'll look at the examples. So actually what happens is for a fair coin toss, if you look at this guy, U1 through UN divided by N, if you remember from your previous lectures, this is just this. So this is just one bit. Basically the joint entropy of the first n symbols is just n times the entropy of the first symbol, and which is one bit. So this is for IID sequences in general, the entropy rate is just equal to the entropy, right? So for IID, entropy rate is equal to entropy. The Markov thing is a bit trickier. Maybe let's just try to compute this one. So let me go through the logic. So the idea is, so if you know U1, so like you can assume, let's say U1 is equal to 0, for example, right? U2 takes two values with equal probability, right? We just saw this example in earlier in class, right? We saw that if U1 is 0, then U2 can be either 0 or it can be 1, each with half of probability, right? So therefore, it's like easy to convince yourself that actually HU2 given U1 is equal to the entropy of a Bernoulli half random variable, right? Because you take two values with equal probability, and this is just one bit. And then what you can convince yourself is that UN given UN minus 1 dot 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 U1 is actually just equal to UN given UN minus 1. And why is this? This is because of the Markov property. Markov property says that if you know the last symbol, the previous symbols have got nothing to do with the next symbol, right? Just the last symbol is the one you care about. And so that's it. Basically, you get the entropy rate as 1 bit. Let me pause here for a second. There is a quiz question very similar. I think feel free to like compute these carefully. Let me just write it clearly. So for IID, there is like a entropy rate written in different ways depending on the text. I will just like try to use a boldface italics type U, is equal to the HU1 basically. For IID, the entropy rate is just the entropy of each symbol. For kth order Markov in general, the entropy rate is the entropy of the k plus 1th symbol given the first k symbols, right? So in these cases, the entropy rate is easy to compute. And basically the idea is that if you know the past k symbols, how much uncertainty is in the next symbol. That's the whole idea here. Let's look at a real example. English. So you can take a lot of English text like a big corpus, and then what you can try to do is try to estimate the probabilities, like you estimate the probability distribution, right? You make a probability model out of English. You take 2 symbols at a time, you take 3 symbols at a time, three characters at a time, 4 characters at a time, so on, and you make this probability table. So what you could do is you could like find probability of U, or you can find probability of U1 comma U2, like 2 characters at a time, or you do like U1, U2, U3, and so on. So you can like make more and more complicated models of English. You can just like, so for example, how would you estimate this? So if you do like, what is the probability that U1 is A and U2 is C? So this will be like number of times you have seen like some xn equal to A and xn plus 1 equal to C divided by total sort of thing, right? So you just estimate, empirically estimate, right? If you have seen this AC combination a million times out of a billion times, then you do like million by billion sort of thing. So somebody did this for some English corpus, and what they found was if you assume it's IID, so 0th order Markov chain, they got like 4.76 bits per letter. So this is like what they got. And as you might imagine, as you take more and more history, your uncertainty will reduce more and more, right? Because you can use that to predict the next symbol. So if you take a first order Markov chain, so if you use the previous symbol to predict the next symbol, so now suddenly you can use the fact that after a Q, you mostly get a U sort of thing. And suddenly you do slightly better. You do like 4.76 to 4.03, right? So your entropy rate, or the conditional entropy reduces, okay? Maybe you take four previous characters. For example, if you see like THI, then you know it's a this or it's a thing, so N. So you are like even more certain about your prediction, and the entropy reduces further. It becomes 2.8. And then Shannon in 1952 actually did a very interesting experiment where he like got a few people, I think his wife actually, but he got some like test subjects basically, and they gave him like up to some symbols in some English text and asked them to predict the next symbol. And then they predicted the next symbol and they say like what is the probability of, like did they predict the right one or not? And then you predict the next symbol. They got a human to actually like predict each symbol, and they use that to estimate the entropy in English, how much uncertainty is in English, assuming that a human is a perfect predictor. And they got 1.3, right? You see like a fourth, it's much better than a fourth order model, and which is true, right? Like the previous word tells you a lot about the next word. The previous sentence tells you a lot about the next sentence. So the dependence is like, goes a bit farther than just 4 characters. And obviously now LLMs have beaten humans. So yeah, if you look at the latest models, we'll look at them in the next lecture. They get a rate which is even lower than this. So they have become even stronger predictors of English than humans at this point. Subject to like the experiment being like done in a specific way. Anyway. Okay. So last slide for today. Just in the previous one you saw it, we said bits per letter, and I've been using compression analogies all the time. So basically kth order Markov source, the best compression you can do is basically this, the HUK given UK minus 1 ... U1. And in general, for a stationary source, entropy rate is the best compression you can hope to achieve. This is the takeaway. So just like the AEP property or typical sets that you read about in lecture 5, there is a similar property called Shannon-Macmillan-Bremen theorem, which says that the probabilities of these blocks are roughly equal to the 2 power minus entropy rate. So it's exactly the same property you saw before, just replace entropy by entropy rate. You need some technical conditions which we won't go into. But basically, that's why these quantities are important, because again, they give us the best you can do in terms of compression. Right? If you have a first order Markov source, then HU2 given U1 is the best compression you can get. And if you have a general stationary source, the best compression you can get is the entropy rate. So next lecture, what we are going to look at is, we will actually see how we can achieve this entropy, this conditional entropy. How do we work with these dependent sources? And we will look more into, first we'll start simple, just first order. Then we'll go to like kth order. And then we'll just say any stationary source. So just rapidly increase the generality of our ideas. And we will use arithmetic coding, as you might have guessed. Okay. Thank you. Happy to answer any questions.